Because I'm using a different computer today, so.
Oh, okay. Do you have GoToMeeting on this computer?
Yes.
Okay. Obviously, otherwise you wouldn't be in this meeting, huh?
Yeah.
So what are we doing tonight?
um, more review for final.
Okay.
Okay, so we have determine the degree of the polynomial using finite differences and find the regression. And so we're looking at a sort of a table function. So it goes 1, 2, 3, 4, 5, 6 in the top row. And then below it, 1, 9, 23, 43, 69, 101.
Like that?
Yes.
And that's all?
Yeah, and then it asks for the degree, the type, and yeah.
Okay.
I know for finite differences, we subtract or add the numbers. Like I would subtract 1 and 9, and then I would subtract 23 and 9, and then I would subtract 23 and 43.
Okay.
And then do the same step until we get the same number. So 8 from 14 is going to be 6. 14 from 20 is going to be 6. 20 from 26 is going to be 6.
Oh,
So
okay. Yeah. Now I remember this. Yeah. This technique. I don't run into this very often anymore.
mm-hmm.
So the fact that we had to go 2 levels down means what?
I'm not sure.
I think that means that it's x cubed.
It's a cubic.
I think so.
So the type would be cubic. Yeah. Because
If we
that's what I
only
have.
had to go, in other words, if we got the same number after doing that step only, or rather this first step, it would have been a quadratic, I believe. I'm not 100% sure. Do you have any way to find out the answer? Because if we knew the answer, we'd be 100% sure. In other words, it wasn't the first step that gave us the same number. It was the third step. So I'm guessing. I don't know, to be honest. Let me think for a second. Yeah, notice that is 1 more than 2 cubed. That is not 1 more than 3 cubed. So I see the technique is to subtract the numbers and keep going until you reach the same number.
Uh-huh.
The question is it, if it's 2 steps to get there, is that a cubic or a quadratic?
I can follow up with my teacher on that.
All right.
But what does it mean when it asks for the degree?
Well, if it's a cubic, it's the 3rd degree. If it's a quadratic, it's 2nd degree. In other words, the degree is the highest exponent.
Okay. So, but then when it says type, I'm assuming that's like cubic, quartic.
Yes.
Okay.
It's a quadratic.
And then
if it's degree.
I'm not.
Go ahead.
Do you know the website that allows you to do like the N-Spire calculator calculations, like the putting in a regression, or putting in the data from this to find the regression equation?
Well, I think Wolfram Alpha does that,
Okay.
but I'm not sure how.
Okay.
Do you know how to do it in your calculator? Do you have an Inspire?
Yeah, I do. I do know how to put it. I do know how to put it in. I was just this is one of the smaller topics, so I wasn't
So
really
if you
too
put that first row in, you'd get a linear regression. Not the first row, not the 1, 2, 3, 4, 5, but the second row of numbers. And then if you put the second row in, that should be quadratic. The third row should be cubic. And we were on the third row where all the numbers were equal. But I hate to talk about that because I really don't come across that often enough. And it's been 5 years since somebody gave me a problem like that. So
Okay.
I'm not 100% sure.
All right.
In terms of regression, linear regression, what we're talking about is if we had points like this. Say you had a bunch of data points like that.
Yeah.
The linear regression is the line that is the best fit through those data points.
Yeah.
Might be that, but it might be that. And there is a mathematical way to figure it out. It's by taking that distance, squaring it, and minimizing it. And that's what your calculator does when it does a linear regression, is it finds the line where the distance from the data point to that line squared, the sum of them is a minimum. Okay, so that's how they find linear regressions.
Okay.
Now, in the Inspire, I haven't done it in an Inspire, but you have to create two lists, your X and your Y points. And by the way, on that table you were giving me, was anything X or Y?
No.
Okay. All right. But the way you do a linear regression is you put in two lists and then you request the linear regression and it'll give you the equation of the line that represents the best fit to those data points.
Mm-hmm.
Now, what I'm thinking is what you were really looking at was here was your top row. Am I wrong here?
No, I think that's what it is.
And then the other one was 1. What was the second point? 9. The third point was 44.
43.
43. What was the fourth point?
9 and then 101.
And then it wants the linear regression of that.
It wants to find the regression equation, yes.
Yeah. It doesn't have to be linear. In other words, you can have linear regression, you can have quadratic regression, you can have cubic regression. In other words, if I were to do a linear regression through those points, that looks pretty linear.
Mm-hmm.
But let's say I had points like this. Now, you could say, okay, I can do a linear regression, come up with a line like that, but a quadratic regression actually appears to go through those points better.
Mm-hmm.
And so when they say find the regression, that's kind of dependent on you knowing whether it's a linear, quadratic, or a cubic degree.
Mm-hmm.
Let's see. It could definitely be quadratic. It could look like that. cubic would look something like this. So it could also be that. So, okay, here's what you have to do. You have to, first of all, you have to determine whether we're looking at a cubic or a quadratic. Pretty sure that it's one of them. Pretty sure it's cubic. And then put in your two lists of numbers and go in and ask for a cubic regression. And it'll give you something that is an x cubed. In other words, those data points that we were looking at look like they could follow that, but they also look like they could be part of a quadratic easily enough. I'm pretty sure they're not linear. We had to go too many steps to get to where all the numbers were equal. I think if it's linear, yeah, if it was linear, yeah, here, we can figure this out, actually. In other words, if something was linear, it would look like that. And when we subtract the numbers, the very first level, we get all of them are equal. I don't know what's going on with this 3, but oh, that's what's going on with it. In other words, if we had a linear function, we would have found the same numbers after one try. We didn't find the same numbers until how many tries?
3 or 2?
I think 2. We got it on this try here, didn't we? What was it? It was 1943.
Yep.
So that's 8, 34. No, there was a number between 9 and 43. Wasn't there?
Yeah, between 43 and 9 was 23.
So it was 23. So this was 14. So we didn't find it in the, if we'd have found all the numbers to be equal there, it would have been linear. It was the next level, so it's quadratic. And what you want to look for is a quadratic regression. And that is going to be degree 2.
Okay.
Okay? Yeah, I'm pretty sure about that. That if you get it right away, all the numbers are equal, then you have a linear equation. If it's one step down, you have quadratic. If it's 2 steps down, you have cubic. And we had to go one step beyond linear. So that should be quadratic. And put those numbers, in other words, make that list 1, make that list 2, and request a quadratic regression.
Okay.
Now, there is a website, Wolfram Alpha will allow you to do it. It's just I'm not sure exactly how to do it on Wolfram Alpha. And you don't need to do it on Wolfram Alpha anyway, right? You need to be able to do it on Inspire. Yeah, and Wolfram Alpha is not exactly the same. Actually, you know, I've been dying to find out where I can get a virtual TI Inspire. I discovered a TI-84 virtual one online once, but I've never found the Inspire. So if you find out what website to get that, please let me know. I'd like to get it. I'd like to put it on my computer.
I know there's one our teacher uses on the smart board, so I'll see if that's something.
What that one is, and if you can give it to me, that would really be helpful to me. because
Okay.
a lot of times I'm trying to teach people how to use a TI Inspire, and it's nice having a virtual one. It was very useful when I had the TI-84 and people needed to know how to do that, but now pretty much everybody uses the Inspire. So
I think it might be Desmos. I'm not sure. I remember that name.
DESMOS?
DESMOS.
No, let's give it a shot. Not that we want to waste too much time. DESMOS?
Mm-hmm.
Oh, well, I bet that is it. .com?
Yeah, I don't know. Graphing. There's different kinds of calculators on the website.
I think this is it. Oh, I want to save this for sure. Let me save this as a favorite. Yeah. Yeah, this looks a little bit like Wolfram Alpha. I'll have to explore it. Looks like here's your scientific calculator down here, or graphing calculator.
Uh-huh.
I don't know if it's a TI Inspire clone, but probably.
Okay.
All right, well, good. We won't get into that now.
All right. So the next thing we have to work on is I can determine if the equation is an odd or even function,
Okay.
or neither, and give evidence to support the answer.
Okay.
So the first one is f of x equals 2x squared plus x minus 6.
How do you tell if a function is odd or even?
I do not know.
Okay, well, that's where we need to start then. Odd functions are where f, the thing you have to check is what is f of minus x? If f of minus x equals minus f of x, you have an odd function. If f of minus x equals f of x, you have an even function.
Mm-hmm.
And if it's neither, anything else is neither. Let's take a simple one. Y equals, and the reason I take this one is because it's got an even exponent.
Mm-hmm.
That is an even function. Why? Because if I substitute minus x for x, I still get x squared. In other words, f of x is equal to x squared, and f of minus x is also equal to x squared. So it satisfies that even function. If I start with a function that I know to be odd, because of the odd exponent there, then g of minus x equals minus x cubed, which equals minus g of x. So these two situations over here on the right, make sure you understand what I'm doing there.
Uh-huh.
I've written a function, and then I've checked what f of minus x is. And it's the same function. That's even.
So
In the second case,
this function is going to be even.
well, no, we have to figure it out. It's not based only on that first term. In fact, those other terms make a big difference. Okay?
Okay.
You can't ignore them. It's not like end behavior where you can ignore everything but the biggest degree. So what we need to figure out is what is f of x or f of minus x. So tell me.
Minus, in parentheses, minus 2x.
No. What we're going to do is wherever we come across x, we're going to substitute minus x.
Okay, so 2 minus x?
2 is all by itself. Now we're going to substitute minus x there.
Oh, I see.
Plus a minus x minus 6. Well, what does this give us? 2x squared minus x minus 6. Well, that is neither f of x nor negative f of x. It certainly isn't f of x, correct?
No, it is not.
Well, what would negative f of x be? Negative f of x would just be a negative sign in front of all of these. So negative f of x would be that. So it's not f of x, it's not negative f of x, therefore it's neither. It's that simple.
Okay.
It's one of the three. Most functions are neither. You have to have a fairly unique type function so that f of negative x is either equal to f of x or equal to f of or minus f of x. These functions over here are nice and simple, so they follow the rule nicely. But this function, because it has that plus x, kind of screws everything up.
Okay.
But that's the test, is f of minus x.
All right.
If you have any other of those, it'd be kind of nice to do one that actually is either odd.
Actually, I have 2 more.
What's that?
I have 2 more. Oh. Negative 3x cubed plus 2x. And that's the first one.
Okay. Now notice what we're looking at. We're looking at odd exponents on both the x factors. That's significant. That means we're probably going to end up with it either being odd or even. So, there's our test. What is that?
Negative 3, and then in parentheses, negative x cubed plus 2, and in parentheses, negative x.
Now, if we simplify that, we have 3x cubed minus 2x. Well, what would negative f of x be? If this is f of x, what's negative f of x?
So the 2 steps are to substitute x for negative x, and then...
No, the other way around. The first step is always substitute negative x for x. And then see what you have. Now, the second step is to see if that is either f of x or negative f of x. It's not f of x for sure, but it is negative f of x. In other words, if I put a negative sign in front of both of those terms, I get 3x cubed plus 2x. Or minus 2x, which is that. In other words, f of negative x is equal to negative f of x. That makes it odd.
Okay, so the next one we have
let's make sure we do one more. Sounds like you're still not certain.
F of x equals x squared. That's it.
Okay, well, that's an easier one. So what's the first step? Figure out what f of negative x is.
Yes. So it will be, in parentheses, negative x squared.
Which is equal to what?
Isn't it just equal to x squared?
which is equal to f of x.
F of x, which is even, correct?
That makes it an even function.
All right.
This is a good one to remember because that is an even number. So if you always can associate the exponent with whether it's even or odd, that'll help. Because sometimes you get the functions like sine x, which is odd, and cosine x, which is even.
Okay.
There's one other thing. Even functions are symmetrical about the y-axis. There's your x squared right there. Odd functions are symmetrical about the origin. There's your x cubed right there. Notice that it's symmetrical about the origin, not the x-axis, not the y-axis, but the origin. In other words, I got to flip over both axes to find symmetry at the origin. You with me?
Yes.
Okay. And even though you haven't had trig yet, the cosine function looks like that. Perfectly symmetrical about the y-axis. That's why it's even. The sine function looks like that. Perfectly symmetrical about the origin. That's why it's odd.
Okay.
But the two to remember are x squared and x cubed, because that way you know for sure what those are.
Okay. Let's do, can you create like a hard one, you would say? Or is there anything hard?
Yeah, the hard ones, it would be hard to create a hard one because working in reverse. The one thing I notice is that if you have nothing but odd exponents, that's going to be an odd function.
Mm-hmm.
If you have a combination of exponents, that's going to be neither. Because notice that when I plug in minus x for x, I still get x squared, but I get minus x, which is neither f of x nor minus f of x. Minus f of x would be minus x squared minus x. That would be minus f of x. Plus f of x would be that. Mm-hmm. So this thing that I get when I plug in minus x for x is neither.
Mm-hmm. Okay.
That's the thing to look for, is if you have both odd and even powers in your polynomial, it's almost certainly going to be neither. If you have all of the same, let's say you have an x to the fourth plus an x squared plus an x to the sixth, they're all even numbers. That's going to be an even function, even if I have a number on it, like that. Because notice that if I plug in minus x, I get the same exact thing.
Mm-hmm.
Now, if these were all odd, notice that that is not going to be an odd function. Because I'm going to get minus x to the seventh, minus x to the fifth, minus x to the third, plus 10.
Mm-hmm.
So that is not the original function, and it's not the negative of the original function, which would be a minus 10.
Okay. I am going to look at my review packet. I'm going to go to the restroom really quick, but I'm going to pick a topic off of the review packet here.
Okay. Go ahead. Take a break if you need one.
Yeah, I'm going to bring it with me. I'm going to go to the bathroom, and then I'll be back in a second, okay?
Okay.
All right.
Nathan?
Yes.
Let me add one more thing before you go on.
Okay.
What can be helpful here is if instead of the first step taking f of negative x, figure out what negative f of x is.
Okay.
F of x is x minus 9. What is negative f of x?
Negative x plus 9.
Yeah, exactly. Negative x plus 9, which is also 9 minus x. Okay, now we'll do our test. In other words, now we know what f of x is and we know what negative f of x is. So let's test this function. What do I get? What's f of minus x?
In parentheses, minus x minus 9.
No, it's minus, yes, excuse me. Yes, you're absolutely correct. Okay, notice that that is not this. It's not that, so it's not negative f of x, and it's not f of x. So that function is neither.
Okay.
Okay? It's got to be either f of x or minus f of x. Come on in. Come on. All right. So that's all I wanted to say is sometimes it's easier because part of the problem is figuring out whether you're looking at negative f of x. It's really easy to tell you're not looking at f of x. In other words, it's real clear that that is not f of x.
Okay.
Right? But it's not super clear that it's not negative f of x. So actually the first step to the problem maybe is figuring out what negative f of x is. And the way you figure out negative f of x is you put a negative sign in front of the whole thing like that. There's f of x, there's negative f of x. And then take away the parentheses, you have minus x plus 9, which is what we got. Okay, so that's negative f of x, and that does not equal that.
Okay.
Okay?
So what I want to go over next is I want to review multiplying and dividing, and adding and subtracting complex numbers.
Okay. There's only one of those things that's hard to do. That's dividing.
Yeah, specifically dividing.
Okay. Let me just go through a couple to make sure you know how to do adding. Add those two.
7 plus I.
Okay. Subtracting. Subtract those two.
negative 1 plus 3i.
Okay. Multiply them by foiling them.
Okay. 3 times 4 is 12. 3 times negative I is negative 3i. 2i times 4 is 8i. 2i times negative I is negative 2i squared.
That's the key. I
Okay.
squared is always convertible to negative 1. In other words, I is equal to the square root of minus 1. So I squared has to be minus 1.
All right.
Now substitute minus 1 for I squared. And you get 14 plus 5i.
So I can always be substituted as minus 1. Or I squared.
Only I squared, not I. Notice I still have an I in my answer. In other words, I was able to combine those two i's to come up with 5i, but this I squared became a minus 1. And that is the key on all of these problems, is convert your I squareds to minus 1.
Okay.
Okay, now the only one that's hard is the division, because you're not really doing division. Let's divide these two. I have 3 plus 2i divided by 4 minus I. Now, when I say you're not really dividing them, that's exactly what I mean. In other words, if I said do this, are you dividing by square root of 2?
No, you're
going to rationalize it, right?
Yeah.
In other words, you're actually going to do multiplication. Same thing with complex numbers. You're not going to divide this. What you're going to do is, the only thing wrong with that as an answer is that you have an imaginary denominator. Well, mathematicians don't like imaginary denominators any more than they like imaginary irrational number, or any more than they like irrational denominators. The reason that is not acceptable is because square root of 2 is irrational. So this is not a division problem, it's a rationalization problem. Same thing with this. It's not a division problem, it is a realifying problem. We need to turn the denominator into a real number. And the way you do that is always by multiplying it by its conjugate. If I multiply 4 minus I times 4 plus I, I'll end up with nothing but numbers and I squareds. In other words, I'll end up with nothing but a number. And since I have to multiply the bottom by the conjugate, I got to multiply the top by the conjugate. That is the number 1. And I can multiply any fraction by the number 1 without changing its value. So, let's figure out the bottom. What's the bottom equal to?
4 times 4 is 16. So
the two middle terms disappear. So you end up with 16 minus
I squared.
What is that number equal to?
16 plus, so it would be minus 1, but then wouldn't it be plus 1, so it would equal 17?
Exactly. And now for the numerator, go ahead and multiply them.
4 times 3 is 12. 2i times I is 2i squared, which will equal...
Hold on, there's two middle terms here. You got to FOIL it. That times that, that times that.
So plus 3i. 2i times 4 is 8i. And then 2i times I is 2i squared.
Okay, now simplify the numerator.
I squared is negative 1, so it'll be plus 1 instead of 2i squared.
It'll be plus 2.
Oh, I'm sorry.
It'll be minus 2, excuse me.
Yes, because we multiply I squared by 2, which would be -1 times 2, which is -2.
Right. Add it to 12, you get 10.
Plus
Combine those I terms, you get plus 11I, and the denominator is 17. So it doesn't look anywhere near like our original problem looked, nor will it ever. Is all we've done is manipulated it so that we have a real denominator.
Uh-huh.
Now let me say one last thing about that answer. If they are insisting that your answers be in A plus BI format, and sometimes they will, the instructions will say put your answer in A plus BI format. That answer is not in A plus BI format. What do I have to do to get it into that?
Um,
I'll give you a hint. Split it into two fractions.
okay, so 10 over 17 and 11I over 17. I remember this.
Plus 11 over 17I.
Oh, okay.
In other words, A is this number, B is that number, and then you have an I. So it's A plus BI. This might be accepted. You may not lose points on that answer all in the lower right. It depends on whether they have requested it in A plus BI format or not. If they don't, then that's a perfectly fine answer. 10 plus 11I over 17.
Okay.
Okay, so you can see adding and subtracting is really easy. Multiplication is easy. Only trick you have to remember is that when you're dividing, multiply the bottom by the conjugate. And since you're multiplying the bottom by the conjugate, you got to multiply the top by the conjugate. If that was 4 minus 2i, it'd be 4 plus 2i. Conjugate is the same two terms, just the opposite sign.
Okay. All right, so next I want to look at identifying transformations within a function.
Okay.
So the equation or the function is y equals -1/2, and then in parentheses x minus 6 squared plus 8. And it says list the 4 transformations for the following function.
Okay. What's the parent function?
I remember the term parent function, but I just can't.
It's the most basic function without any of those transformations. So here's your transformations. There's 1, there's 2, there's 3, there's 4. Take them all of them away and you have your parent function.
So it's x squared. Okay, so it's just x minus 6?
No, it's x squared. Okay. Don't take away the 2. What you're taking away is the negative sign. You're taking away the 1/2. That's a transformation. You're taking away that. That's a transformation. And that's the 4th transformation.
Okay.
So the only thing you're left with is x squared. I don't want to call it y because it's not the same as this y. This y is transformed of g of x.
Mm-hmm.
So now what we have to do is figure out what each of those transformations does. What's the first negative sign do? I'm going to go left to right.
I totally have forgotten like all
Negative signs are either vertical reflections or horizontal reflections.
Okay.
If it is outside the function, it is a vertical whatever. If it's outside the function, it's vertical. In other words, that is outside the function, it's going to be a vertical reflection. If it's a vertical reflection, which axis is it reflected over?
The x, right?
Yeah. If I have a parabola, and I'm going to reflect that vertically, it's going to look like that. and I'm reflecting it over the x-axis. Now, there's a reason I call it a vertical reflection. It's important. There are only 6 types of transformations. There are 3 vertical and 3 horizontal. All vertical transformations are outside the function. All horizontal transformations are inside.
Okay.
So the negative sign is outside the function. That makes it a vertical reflection, which is a reflection over x.
Mm-hmm.
And always do your reflections first. The rest of the order, you can do them any way you want. But if you're graphing this, you're starting with x squared, do a reflection first before you do these other 3 transformations.
Uh-huh.
Okay, so that's the negative sign. Second transformation is this 1/2. Is that inside or outside the function?
Outside.
Okay, does that make it vertical or horizontal?
Isn't it vertical?
Everything outside is vertical, so it's a vertical something. Now, it's multiplying the x minus 6 squared. Multiplier means it's a stretch or a shrink.
Okay.
If it's greater than 1, it's a stretch. If it's between 0 and 1, it's a shrink. So this is a vertical shrink by 1/2. You with me?
Yes.
The next thing is this negative 6. Is that inside or outside the function?
Inside.
Makes it horizontal. Right? Everything inside is horizontal, everything outside is vertical.
Correct.
Now, the standard is x minus h. So in this case, h would be a positive 6. Positive means shift to the right because we're adding or subtracting. We're not multiplying that 6 times x. We're subtracting 6 from x. So it is a horizontal shift, not a stretch or a shrink, a shift. When you do a shift, you don't change the shape of the curve. You just move it either over, left, or right, or up and down. So the only thing you have to know here is it to the right or is it to the left? And it's to the right because it's a positive 6. Because the standard is x minus h. So when you see an x minus 6, h is positive 6. Positive means go to the right, negative means go to the left.
Mm-hmm.
Finally, we have this plus 8, inside or outside the function?
Outside.
It makes it vertical. Is it multiplying or adding?
Adding.
That's a shift. Is plus up or down?
Up.
So over here, I'm going to plot the parent function first. Then I'm going to do each of these transformations one at a time. The first one is the reflection. Always want to do your reflections first. Doesn't matter what order you have them. You can have 2 reflections. You can have a reflection over the x and the y. You would do both of them first.
Okay.
And then you do everything else. Okay. So the half. The first one, this is just, if I want to label that, that's minus x squared. Okay?
Mm-hmm.
Second, we're going to do that one. We're going to take our blue line and we're going to shrink it. Now, a stretch or a shrink changes the graph, the shape of the graph.
Mm-hmm.
A shrink flattens it. A stretch makes it skinnier. So that is a shrink by 1/2, the green line. That I would label minus 1/2 x squared. With me?
Mm-hmm.
Next, we're going to do the minus 6. That's a horizontal shift to the right 6 units. So I'm going to take my vertex, which has not changed in any of the two previous transformations, but now I got to shift it to the right by 6 units so that it's over here. Okay? Shifts do not change the shape of the curve. That curve stays exactly the same shape as the green. Doesn't get skinnier, doesn't get fatter. Because all I did was I moved the green curve 6 units to the right. Finally, the last thing I'm going to do is I'm going to take this plus 8 and I'm going to move my purple up 8 units. Again, does not change the shape. That's supposed to be the same shape as the purple. It's not skinnier or fatter. Shifts do not change the shape. Shrinks and stretches do.
Okay.
Okay. Now, this is a really important topic. Before I leave it, I'm just going to give you a couple of things and ask you what they are. Okay. So we're going to make our parent function the same parent function, x squared. So tell me hold on. What is that? What's that negative sign mean?
Well, it's on the inside, so it's horizontal.
Which means
That
the
it's
reflection over the y-axis.
y-axis to the left because it is a negative.
Ah, it's just a reflection over the y-axis.
Oh, okay.
Like
So
that
it's
over
not
the y-axis, what do I get?
the same thing.
Aha. And if I do the math, what do I get? The same thing. In other words, when you're dealing with this parent function, x squared, a horizontal reflection doesn't change anything. Because it's an even function, first of all, and even functions are symmetrical with the y-axis. So you would not expect a reflection over the y-axis to do anything to an even function. Okay, you with me?
Okay.
Hold on. Not quite done. Yeah, there's one other that I want to talk about. Is that horizontal or vertical translation?
It is a horizontal because it's inside of the...
Exactly. So what does the 3 do? It's not being added or subtracted, which would make it a shift. So it's got to be either a stretch or a shrink, right?
Uh-huh. And it's positive, so it's a stretch.
Actually, it's the opposite of the other case. They're opposites. If it is a vertical and it's greater than 1, it is a stretch. If it's between 0 and 1, it's a shrink. But if it is horizontal, it's the opposite. This is actually a shrink.
Okay, that makes sense.
By a factor of 3. Well, it definitely makes sense if you graph it out. Just remember when you're thinking about it that they're opposite. In other words, if it's 3x squared, it's a stretch by a factor of 3. But if it's 3x quantity squared, it is a shrink by a factor of 3, and it's a horizontal shrink. Now notice that horizontal shrinks. If I take a horizontal shrink to that parabola, I turn it into that. In other words, I'm pushing on it from both sides, right?
Right.
Notice that a horizontal shrink is the same as a vertical stretch. In other words, if I take the original parabola and I vertically stretch it, it gets skinnier. So my vertical stretch and my horizontal shrink are actually similar in the way they change the graph. They either make it skinnier or fatter. But when you're thinking horizontal shrink, what you're doing is pushing both sides in. So it makes the curve skinnier. Now, these two aren't exactly the same because this one ends up being 9x squared. This one ends up being 3x squared. So they're not, it's not exactly, in other words, a shrink by a factor of 3 is not quite exactly the same as a vertical stretch by a factor of 3. It's actually greater. Makes it 3 times as skinny. A horizontal shrink by a factor of 3 makes it 3 times skinnier than a vertical stretch by a factor of 3. Oddly enough, but that's true. All right. When's your final, Nathan?
Next Friday?
Okay, so we got plenty of time.
Yeah.
All right, well, I will let you go. I'll let you go for tonight.
All right.
All right.
Have a good night.
Bye-bye.